Nanoscience, the study of fundamental particles of nanostructures between bulk and atomic properties. Nanotechnology is the application of nanostructures into useful devices. So nanomaterials and structures. So nanomaterials and structures are fabricated in one dimension. Nanoscale. In nanomaterials and nanostructures, we have nanoscale in one dimension, nanoscale in 2 dimensions, and nanoscale in 3 dimensions. Nanoscale in 1 dimensions, we have thin films, layers, and surfaces. One-dimensional nanomaterials such as thin films and engineered surfaces have been developed and used for decades in fields such as electronic device manufacturing, chemistry, and engineering. Silicon IC, integrated chip circuit industry, silicon IC circuit industry. Many devices rely on thin films. For their operation and control of film thickness approaching the atomic level is routine. If you go for monolayers, layers that are one atom or molecule deep are also routinely made and used in chemistry. The formation and properties of these layers are reasonably well understood from atomic level upwards, even in quite complex layers such as lubricants. Advances are being made in the control of the composition and smoothness of surfaces and the growth of films. That means thin films are grown on the substrate. So to a few micron level or few nano level, right? So we have a substrate, right? We have a substrate like glass substrate. You can have aluminum substrate. You can have a plastic substrate. We have a plastic, the transparent sheet substrate. Plastic transparent sheet, where the thin films can be deposited. On that particular substrate to a few micron layers. So that is what thin layers added to a surface. So the thin layer that is added to a surface is of thickness of few microns or less. So that is what we can see in the figure. So that is what nanoscale in 1 dimension. Thin films, layers and surfaces. That is 1-dimensional nanomaterials such as thin films and engineered surfaces have been developed and used for decades in fields such as electronic device manufacturing, chemistry and engineering. Silicon integrated chip circuit industry. Many devices rely on thin films for their operation and control of film thickness approaching the atomic level is routine. Monolayers, layers that are one atom or molecule deep, are also routinely made and used in chemistry. The formation and properties of these layers is reasonably well understood from atomic level upwards, even in quite complex layers such as lubricants. Advances are being made in the control of the composition and smoothness of surfaces and growth of films. So engineered surfaces with tailored properties such as large surface area or specific reactivity are used routinely in a range of applications such as fuel cells and catalysts. The large surface area provided by nanoparticles, together with their ability to self-assembly on support surface, could be of use in all these applications. Although they represent incremental developments, surface with enhanced properties should find applications throughout the chemicals and energy sectors. The benefits could surpass the obvious economic and resource savings achieved by higher activity and greater selectivity in reactors and separation process. Greater selectivity in reactors and separation process. Another use could be the small scale, right? Small scale on-site production of high-value chemicals such as pharmaceuticals. That is what engineered surface with tailored properties such as large surface area or specific reactivity are used routinely in a large application such as fuel cells and catalysts. The large surface area provided by nanoparticles together with their ability to assemble, to self-assemble on a support surface could be of use in all these applications. Although they represent incremental development surface with enhanced properties should find application throughout the chemicals and energy sectors. The benefits could suppress the obvious economic and resource saving achieved by higher activity and greater selectivity in reactors and separation process. Another use could be the small scale on-site production of high value chemicals such as pharmaceuticals. So now if you see the nanoscale in 2 dimensions, two-dimensional nanomaterials such as tubes in the sense like carbon nanotubes and wires and nanowires have generated considerable interest among the scientific community in the recent years. The two-dimensional nanomaterials such as nanotubes and wires have generated considerable interest among the scientific community in the recent years. In particular, their novel electrical and mechanical properties are the subject of intense research. In particular, their novel electrical and mechanical properties are of the subject of intense research. Right. So, other is the carbon nanotubes. That is what we are talking about. The two-dimensional nanomaterials like tubes and wires. Right. So, the first carbon nanotubes were discovered in the year 1991 by Sumio Ijima. And they are extended tubes of rolled graphene sheets. So these carbon nanotubes are of two types. One is a single wall nanotube and another is a multi-walled nanotubes. So single wall nanotube in the sense one tube we have, a multi-walled nanotube is several concentric tubes in the sense tube inside a tube. This is our nanotube. So there is a tube inside the tube. Right. So this is what the multi-walled several concentric nanotube. So both are a few nanometers in diameter and several meters to centimeters long. So the important role because of novel chemical and physical properties. Both are few nanometers in diameter and several milliseconds to centimeters long. So the dimensions are a few nanometers in diameter and several meters to centimeters long. So important role is because of novel chemical and physical properties. So we have different types of carbon nanotubes. That is what we have. We are talking about a single wall nanotube and multi-wall nanotube. So in a single wall nanotube, so we can see here this is our single wall nanotube. This is a nanotube. So this is a single wall nanotube. And the length is approximated to several microns. The length is approximated to several microns. And the diameter of single wall nanotube is 1 to 2 nanometer. The diameter is approximated to 1 to 2 nanometer. That is single wall nanotube. That is up to 50 nanometer. Multi-wall nanotube is interlayer distance is approximated to 0.34 nanometers. Multi-wall nanotube is approximated interlayer distance of approximately 0.34 nanometers. So this is another is called a fullerene, or we already call it as buckyball. So fullerene or buckyball. Buckyball is similar to nothing but a football, right? So this is what multi-walled carbon nanotube. That is a tube inside a tube. That is what concentric tubes. This is one tube. We can see here yellow color is one tube and red tube, and then we have one red layer outer surface. So that is one tube. So the tube inside a tube is what we call it as multi-walled carbon nanotube. So there are two types of carbon nanotubes as we discussed. That is a single-walled carbon nanotube, that is SWT, and other is a multi-walled carbon nanotube, and that is a fullerene. Fullerene is also one type of a buckyball-like tube, on which we have some different hexagonal and orthogonal structures. And the distance and the dimensions of this tube, length is approximately several microns and diameter is approximately to 1 to 2 nanometers, single wall nanotube, and it approximated up to 50 nanometer, right? So that is a multi-wall nanotube. It is an interlayer. Multi-wall nanotube is nothing but an interlayer, and the distance is approximated to interlayer distance between the two nanotubes is approximately to 0.34 nanometers. Right. If you see for the carbon nanotube, we have unique structures, right? So So unique structures for carbon nanotubes are like thermal conductivity and electric conductivity. The the unique features of carbon nanotube. That means the carbon nanotube have features that the electrical conductivity of carbon nanotube is similar to like copper. The electrical conductivity of carbon nanotube is similar to electrical is similar to copper, and thermal conductivity is like diamond, and thermal conductivity is diamond. So if you see the graph here, if you see the comparison of the tensile strength of single wall nanotube to some common high strength material. So this is what we have. This is stainless steel, right? This is aramid, that is KVR, and graphite fibers. Graphite and diamond are the pure allotropes of carbon, right? So that's why we call it a carbon nanotube. This is a graphite fiber and carbon nanotube, right? The tensile stress, the comparison of the tensile strength of single nanotube to common materials is what is shown in this figure. The strength is 100 times greater than steel at 1/6 the weight and high strain to failure ratio. High strain to failure ratio in the sense the strength of the steel. That is what we tell the Young's modulus. If you speak about the mechanical property, one of the mechanical property is nothing but stress proportional to strain. Stress proportional to strain. Stress proportional to strain. Stress by strain is equal to constant, which we call it as Hooke's law. So which depends upon the tensile stress. It depends upon the tensile stress. Tensile stress in the sense that how much pressure we apply, right? How much we apply the pressure, the tensile strength we apply on single nanotube to some common strength material. The strength is 100 times greater than steel to 1/6 the weight and high strain to failure, right? So there are different types of carbon nanotubes. So they are certain. Some of them certain are inorganic nanotubes and oxide based nanotubes, right? So in inorganic nanotube and inorganic fullerene like material based on layered compounds such as molybdenum disulfide were discovered shortly after carbon nanotubes. Soon after the discovery of carbon nanotube, inorganic nanotube and inorganic fullerene like materials. Inorganic nanotubes and inorganic fullerene like materials. Fullerene like materials is like buckyball materials based on layer compounds, layer compounds such as molybdenum disulfide were discovered soon after the discovery of carbon nanotubes. They have excellent tribological properties. That is lubricating properties, resistance to shock wave impact, catalytic reactivity, and high capacity for hydrogen and lithium storage, which suggest a range of promising applications. Oxide-based nanotubes such as titanium oxide are being explored for the applications in catalysis, photocatalysis, and energy storage devices. It is oxide-based nanotubes. Oxide-based nanotubes such as titanium oxide are being explored for their applications in catalysis and photocatalysis and energy storage devices. And these inorganic nanotubes, and they have very good application for energy storage devices, energy storage devices, and sodium cells, right? So they have excellent tribological lubricating properties, resistance to shock wave impact, catalytic reactivity, and high capacity for hydrogen and lithium storage, which suggests a range of promising applications. Oxide-based nanotubes such as titanium oxide are being explored for their applications in catalysis, photocatalysis, and energy storage devices. So if you speak about the nanotubes being the nanoscale in 2 dimensions, when we study about the nanoscale in 2 dimensions, we have studied about a nanotube, which are the single wall nanotube and others the multi-wall nanotube, and we have seen some of the applications of the inorganic nanotubes and all. Now let us see what are nanowires. Nanowires are also two-dimensional scale nanomaterial. Right? Nanowires are ultra-fine wires or linear array of dots formed by self-assembly. Nanowires are ultra-fine wires or linear array of dots formed by self-assembly. They can be made from wide range of materials. Semiconductor nanowires made of silicon gallium nitrides, and indium phosphide have demonstrated remarkable optical, electrical, and magnetic properties. For example, silicon nanowires can bend light around every tight corner. Silicon nanowires can bend light around every tight corners. Nanowires are potential applications in high density data storage devices. Nanowires have potential applications in high density data storage, either as magnetic read heads or as pattern storage media and electronic and optoelectronic nano device for metallic interconnects of quantum devices and nano devices. Right? So nanowires are ultra fine arrays, ultra fine wires or linear array of dots formed by self-assembly. They can be made from a wide range of materials. Semiconductor nanowires made of silica, gallium nitrides, and indium phosphide have demonstrated remarkable optical, electrical, and magnetic properties. So silicon nanowires can bend light around very tight corners. And these have very potential applications. So nanowires have potential applications in high density data storage devices, either as magnetic read heads or as pattern storage media and electronic and optoelectronic nano device for metallic interconnects of quantum devices and nano devices. I mean, nanowires have potential applications in GMR devices, that is giant magnetoresistive material, that is which storage have density recording storage devices. And GMR devices, GMI, giant magneto-inductive properties, giant magneto-impedance materials, and spintronic-based materials, and also spintronic-based materials, spintronic-based applications. That is why we tell nanowires have potential applications in high-density data storage, either as magnetic read head or as pattern storage devices. So if you see about the nanoscale in 3 dimensions, nanoscale in 2 dimensions, we have seen nanoscale in 2 dimensions called nanoscale in 2 dimensions are nothing but the nanocarbon nanotubes and nanowires. And now let us see nanoscale in 3 dimensions. So nanoparticles are often defined as particles of less than 100 nanometer. Nanoparticles are often defined as particles of less than 100 nanometer in diameter. They exhibit new or enhanced size-dependent properties compared with larger particles of the same material. Nanoparticles exist widely in the natural world. Examples as the products of photochemical and volcanic activity and created by plants and algae. They have been created for thousands of years as products of combustion and food cooking, and more recently from vehicle exhaust. Deliberately manufactured nanoparticles such as metal oxide are by comparison in the minority. That means deliberately manufactured nanoparticles and metal oxide nanoparticles are of less importance. That is what nanoparticles in 3 dimensions. So particles often having the dimensions less than 100 nanometer in diameter, they exhibit a new enhanced size-dependent property compared with larger particles of the same material. Nanoparticles exist widely in the natural world. Example as a product of photochemical and volcanic activity created by plants and algae. They have been created for thousands of years as products of combustion and food cooking, and more recently from vehicle exhaust. Deliberately manufactured nanoparticles such as metal oxide are by comparison in the minority. Nanoparticles are of interest because of the new properties like chemical reactivity and optical behavior. Right, nanoparticles show wide interest because of their chemical reactivity and optical behavior. Right, so that they exhibit compared with other larger particles of the same material. For example, titanium oxide and zinc oxide become transparent at the nanoscale. Titanium oxide and zinc oxide become transparent at the nanoscale, however, are able to absorb and reflect ultraviolet light and hence found applications in sunscreens. That is what nanoparticles are of interest because of the new properties, because of the new novel properties of that is chemical reactivity and optical behavior that they exhibit compared with larger particles of the same material. For example, titanium oxide and zinc oxide become transparent at the nanoscale, however, are able to absorb and reflect ultraviolet light and hence found applications in sunscreen. Nanoparticles have a range of potential applications. In short term, in new cosmetics, textiles and paints. In longer term, in methods targeted to drug delivery, where they could be used to deliver drugs to specific site in the body. Nanoparticles can also be arranged into layers on surfaces, providing a large surface area and hence enhanced activity relevant to a range of potential applications such as catalysts. So nanoparticles can also be arranged into layers on surfaces, providing a large surface area and hence enhanced activity to a range of potential applications such as catalysts. So manufactured nanoparticles are typically not products in their own right, but generally serve as a raw material ingredients and on additives on existing products. Right. So manufactured nanoparticles are typically not products in their own right, but generally serve as raw material. When nanoparticles are manufactured, right? Nanoparticles and nanostructures we can have some commercially available nanostructures also, where the nanostructures can be fabricated by using some different lithographic techniques, where this commercial nanostructures can be fabricated, can be available from IIT Bombay or at Center for Nanoscience and Engineering at IISc Bangalore. Manufactured nanoparticles are typically not products in their own right, but generally serve as a raw materials, ingredients on additives in existing products. Their production is currently low compared to other nanomaterials. The production is very low compared to other nanomaterials. Currently, in a small number of consumer products such as cosmetics, their enhanced or novel properties may have applications for their toxicity. Fixed or free have a significant effect on their potential health, safety, and environmental facts. So, another form is a fullerene, as we told. It's a buckyball, which is of carbon 60. In the middle 1980s, a new class of carbon materials were discovered called carbon 60, C60. Right? So in the middle 1980s, a new class of carbon materials were discovered called carbon 60. We know that carbon and graphite and diamond are the two pure allotropes of carbon. So in 1990s, a new class of carbon materials were discovered called carbon 60, that is C60. So spherical molecules about 1 nanometer in diameter, comprising 60 carbon atoms arranged as 20 hexagons and 12 pentagons, and the configuration of a football. Spherical molecules about 1 nanometer in diameter, comprising 60 carbon atoms arranged as 20 hexagons and 12 pentagons, the configuration of a football. And if we talk about the fullerene in 1990, a technique to produce large quantities of C60. In 1990, a technique to produce large quantities of carbon 60 was developed by resistively heating graphite rods in helium atmosphere. That means the development of carbon 60 was developed by resistively heating a graphite rod in the sense allotrope of a carbon, resistively heating graphite rod in a helium atmosphere. In 1990, a technique to produce larger quantities of C60. In the middle 1980s, C60 was initiated. In the 1990, a technique to produce large quantity of C60 was developed. So this technique of producing large C60 developed is by resistively heating graphite rods into a helium atmosphere. So several applications of fluorines are ball bearings to lubricative surfaces, drug delivery vehicles, and in electronic circuits, where C60 was developed. C60 was developed in a large quantity, right? So several applications of fluorines are ball bearings, that is a buckyball, we call it as ball bearing, to lubricative device surfaces, drug delivery vehicles, and in electronic circuits. So if your next form of nanoparticles are the quantum dots. Nanoparticles of semiconductors, that is quantum dots, were theorized. The theory behind the nanoparticles was theorized in the year 1970s and actually created in the early 1980s. That means the nomenclature for the quantum dots was introduced in 1970, and the experimental fact and their theoretical analysis, when correlated with the experimental fact, was created in the early 1980s. That is, if a semiconductor particle are made small enough to quantum confinement, if semiconductor particles are made small enough, some quantum confinements come into play, which limits the energies of the electrons and holes. Quantum confinement comes into play that limits the energies at which the electrons and holes can exist in the particle. right? So that means that optical properties of the particle can be finely tuned. That means the optical properties can be finely tuned depending upon the size of the particle. Depending on the size of the particle. That's what, if a semiconductor particle are made small enough, if semiconductor particles are made small enough, quantum effects come into play or effect, which limits the energy at which the electrons and holes can exist in the particle, which limits the energies at which electrons and holes exist in the particle. It means that the optical properties of the particles can be finely tuned depending on its size. Thus, particles can be made to emit or absorb specific wavelengths. Thus, particles can be made to emit or absorb specific wavelengths, colors of light, merely by controlling their size. Thus, particles can be made to emit or absorb specific wavelengths, colors of light, merely by controlling their size. So, that is what we need, some of the fundamental facts of quantum dots. Now, recently, quantum dots have applications in composites, solar cells, and fluorescent biological labels, which use both the small particle size and tunable energy levels. Recent advances in chemistry have resulted in the preparation of monolayer protected high quality monodispersed crystalline quantum dots as small as 2 nanometer in diameter, which can be conveniently treated and processed as a typical chemical reagent. So recently, quantum dots have applications in composite solar cells and fluorescent biological label, which use the small particle size and tunable energy levels. Energy levels can be tuned, right? So recent advances, after the advancements in chemistry, are resulting in the preparation of monolayer protected high quality monodispersed crystalline quantum dots as small as 2 nanometer in diameter, which can be conveniently treated and processed as a typical chemical reagent. Right? So these are some of the fundamental facts which we need to understand. That which we need to understand how the nanotechnology imparts or makes the whole nano world. Okay, so in which the bulk materials can be reduced to nano size, and which is having a much similar importance. That's all. So semiconductor nanodots, as you have seen, semiconductor nanodots are nothing but that's what they are theorized in 1970s. So this is what. So that means a quantum confinement, a position of quantum confinement comes into play, which limits energies at which electrons and holes can exist in the particles. This means that optical properties of the particles can be finely tuned depending upon size. Thus, particles can be made to emit or absorb specific wavelengths or colors merely by controlling their size. So that is what the nanocrystals, if you see, they changes its color, right? The changes in color after the developments in chemistry, which is a typical reagent, right? So that is what quantum effect. Crystal size determines the color. That is blue shifted where the colors are shifted when the size becomes smaller. That means when the size becomes smaller, the color becomes red to orange, orange to green, and green to blue. That means when the size becomes smaller, then the color changes. That is what quantum confinement. That is crystalline size determines the color. That is blue shifted when smaller. So if you see the fabrication is nothing but nano materials can be fabricated in two ways. That is top down and bottom up and top down approach. And this top down and bottom approach you can see how this fabricated in nanomaterials, how the structures are manipulated, how nanostructures are fabricated, right? So what are the methods that we follow in top down approach and bottom up process? What are the process that come under bottom up process and top down process? This all we can see in the next coming slides.
Like, share and subscribe. Hit the bell icon for more updates.